But now we're going to make it into centimeters, right? So remember, for every kilometer, there's 1,000 meters, and there's 100 centimeters in a meter, right? So in other words, I'm going to take this number, I'm going to multiply it by 1,000. That gives me meters, but then I want centimeters, so I'll multiply it by 100 times 100. So it's about 0.8. Let's make it, or 0.79. 0.79. That's pretty slow. In the middle Atlantic should be around 2, but we're not too far off. It's about 1 centimeter per year, right? So again, remember the 1,000 meters per kilometer, 100 centimeters per meter, and that gives us this number here. And that kind of works along with that one figure, figure 2 for the rates of seafloor spreading. How much wider, right? So remember, if rate is distance over time, then distance is going to be rate times time, right? And so in this case, we know it's moving at 0.79, 0.79. That's a rate, right? Centimeters per year, and the time, it says, is 100 years. So the years are going to cancel out. We'll get centimeters, because that's what we want. We want the distance in centimeters. So basically, you take 0.79. Yeah, so let's just do that. It's going to move 790. Yeah, almost centimeters. 790. I don't need centimeters. That's almost a meter. Also, that's almost 3 feet. So if someone lives to 100 years old, the seafloor or the Atlantic will get wider by about almost 3 feet, right? So that's what it's telling us there. So anyways, you can check my math on that there. All right, and this next part is pretty interesting in that we're looking at these magnetic stripes on the seafloor. And you can actually go in a ship, measure those magnetic anomalies. You'll get the magnetometer to give you these readings, and the product would be a graph like this. And you can see that for the Pacific Ocean, it's spreading at a faster rate. So we're covering more distance for those same magnetic anomalies. And you can see, you'll find them here in the Atlantic Ocean. They're the same. You can match these two up, right? Except they're closer together here because this has a slower spreading rate than the East Pacific rise in the Pacific Ocean, right? And then note that we're only seeing half, right? So the mid-oceanic ridge is here, and then we're going west on both of these. You would see a mirror image going east as well, but it'd be flipped around, right? So we're only seeing half the ridge there. So on this figure, we want to let's go out to the farthest it goes out. You can see it goes out, well, not quite to 80, but we'll do this anomaly right here, the farthest one. Maybe that's 78, and over here it's the same one, maybe about 78 for the Pacific Ocean as well. And so you can see for the South Atlantic, that takes us about right to here, which is about 1,400 kilometers, right? So 1,000, 11, 12, 13, 1,400. So you'd put that right there. But for the Pacific Ocean, it's taken us to about 3,000 kilometers. So right away you can see that it's almost twice, well, more than twice the spreading rate, right? And both of these are about 78 million years. We'll put MA, 78 MA. Remember, MA means millions of years ago from today, right? So now you can do the math. I'll let you do the math here since I've already done the math in the previous problem. You can kind of figure this out. I'll let you do that. And then you can see what's going on with the date here. I'll let you figure out the North Atlantic, right? And they're giving you 185 million years. And then you can compare those numbers there. And I think, yeah, you should be able to figure this one out. I won't do any more on that. The anomalies are wider because it's a faster spreading rate for the East Pacific rise. Now, when we look at activity 1.7, we're looking at this bathymetric profile. The red colors here are around 2,700 meters deep. The green's 3,800, light blue's 38, 5,000 way out over here. So you can see it's not as deep at the ridges, but it's deeper farther from the ridges. Remember, it's younger. The rock is less dense here. It's still warm, so it tends to rise or float higher in the mantle. As it gets older, it gets more hydrated, more compacted, and colder, and it starts to sink lower into the mantle. So you get these deeper ocean basins here. So we're going to be looking at these, both the Mid-Atlantic Ridge, the Mid-Atlantic Ridge here and the East Pacific Rise here, right? So we're looking at these. So the Rift Valley for this question A, which has the best Rift Valley, you can see that it's kind of hard to make out the Rift Valley in the Pacific Ocean, right? So off of over here, off of Australia and southern South America there. But in the Mid-Atlantic Ridge, I clearly see the Rift Valley. So this one definitely has a better Rift Valley here for the Mid-Atlantic Ridge. For question B, keeping in mind the age versus depth, why is a belt of shallow sea wider? So we just figured that out. So it's wider here because it's spreading at a faster rate. So in other words, the ages of the rocks right here are the same age as these rocks over here in the Atlantic Ocean. But look how much farther away they are from the Rift Valley, from the mid-ocean ridge there. So they're still warm, right? They just, it's taking longer. It's taking just as long to cool, but they're just moving at a faster rate away from the mid-oceanic ridge. And the age of these rocks over here are about the same as kind of this area over here. So again, they're moving much farther away. They're taking longer to cool. All right, so that's that question there. And then, so now for this part, you want to take this graph and place it. And I literally will place it right over the ridge. And we'll do, and I want to do two different colors. Red for East Pacific Rise and green for the Mid-Atlantic Ridge, right? So what you'll do, I recommend just taking your graph here and folding it. And we're doing let's do the East Pacific Rise first. And you can pick any place on this. Just make sure the 0 lines up with the ridge axis. So remember, this is our ridge axis right here. And then you're going to estimate the depths, right? So if we zoom in here, you can see that right at the ridge axis, we're at this red color, red and yellow, and that corresponds to maybe, a little bit less than maybe 2,400, 2,000 feet right in there. So we look over here, well, it looks like we start off at 2,500 here. So we'll be right like in here. And then we'll keep going, and then we'll get to the yellows. The yellows are a little more than 2,700 feet, so that's going to be maybe in here, and I guess right in there. And then as we get to this kind of greenish blue is about 3,800 feet. So 3,800 feet, that'd be down over here. And then the greenish blue is down over here as well. The light blue, which is way over here, is at about, I would say 4,000, 4,500 or so. Well, there it is. So it's going to be way down over here. And light blue is way down. And then you would connect these with, we're using red for the East Pacific Rise. We're using red. Just connect these. And there's our, remember, this is our East Pacific Rise. So you can do the same thing, but you'll bring this over and you'll do it for the Mid-Atlantic Ridge. And pick any line right there. You can pick that one there. Plot your points. Pick any line right there. You can pick that one there. Plot your points. You'll compare East, and remember, you're going to be using green for the Mid-Atlantic Ridge. And then you want to submit this. And then you can answer the last question that goes there. Well, I hope that helps a little bit. You can email me with questions. This lab's pretty straightforward. I know you may have some questions, but I thought I'd help out with this video. But I'll stop here for now.